So we often want to look at how long it takes for populations to double their size or half their size. The time to double a population is related to a fixed fraction of time. So for example, if we have C grams, and C would be our initial amount here, of a substance that doubles every 10 days, then our formula is going to look like this. Y equals C times 2 to the T over 10 power. So Y. So let's just look at the doubles part first. If something doubles, that means it increases by 100%. That means your R would be positive. If you move that decimal over twice, that would be positive 1. So in your parentheses, you would have 1 plus 1. So just know that's where that came from. This 2 is really 1 plus 1 in there. Okay, and then because it says every 10 days, so it doesn't just double every day, but it's every 10 days. So whenever you have a number that's just besides 1 day or 1 year or 1 month, you have to show that it's every so many days. So that means T really stands for a day here. But because it's every 10 days, you have to include T divided by how many other days in that exponent. So T divided by 10. So then if we look at our half-life here, the substance halves its amount every 6 hours. So think about if something halves, it's going to decrease by 50%. So that means your R would be negative 0.5. So in your parentheses, the reason it's 1/2 there is because that's really 1 minus 0.5. And then the reason it's T divided by 6 is because it says every 6 hours. So T is really hours, but because it's every 6 hours, you have to do the hours divided by 6. So anytime you see doubles, know there's going to be a 2 there in the parentheses. And anytime you see halves, know that there's going to be 1/2. And then that's just kind of your reason. So if you look at number 5, the number of bacteria in a petri dish doubles every 4 hours. How long will it take, so we're trying to find T, for 100 bacteria to increase to 50,000 bacteria? Okay, so the 100 here is how much we're starting with, so that's our initial. And then our final that we want it to be is 50,000. So if we write our just equation, P of T equals, our initial is 100. Because it doubles, that means we're going to have a 2 in the parentheses because it would be really 1 plus 1. And it says every 4 hours, so T over 4. Now, just so you know, T is in hours whenever we finish this. Okay, we're trying to figure out when it's equal to 50,000. So we want to put that 50,000 for the final there. So because we're not just plugging in, we're trying to figure out when two things are equal, we're going to use that graph on our calculator. We're going to have y1 and we're going to have y2. So if you pull up your calculator, go to y equals. In y1, I'm going to put my 50,000. And in y2, we're going to have 10. No, that's 100. So 100 parentheses 2 to the exponent. And the exponent is t divided by 4. So x divided by 4. Now I'm going to go ahead and go to my window. I already have x max as 100. I'm going to leave that. But y max here, because it's 50,000, we need to go bigger than that. So I'm going to do 55,000. Let's just see if we can find where they intersect. So we can. So we have like a picture here and here, and we're just finding their intersection. So to do the intersection, you're going to do second, trace, intersect, which is number 5. You're going to enter 3 times. And so that x value or that t value here should give you 35.863. And we'll keep the decimals just because this is hours. Okay, so then the next problem. So if you remember back on, this was really day 2, we looked at the radioactive carbon-14 and we found its half-life to be 5,700 years, but we used an exponential function like they gave us. But we can also do half-life problems like we're about to do, and you would typically do half-life problems like this from now on. So the half-life of radium-226 is 1620 years. Whenever it says half-life, that tells you that in your parentheses you're going to have half. Is 1620 years. And then this tells you like per year. Whenever you have a half-life, they'll give you that. If 20 grams remain in a sample after 500 years, so T is 500, how many grams were in the initial? So we're trying to find the initial this time. Okay, so let's put all this together. So we're going to have P of T equals, we do not know the initial, so I'm going to put P of naught. Because it's half-life, you're going to have 1/2 in the parentheses. And then half-life will always tell you how many per year, so that's going to be T over. And then the half-life is 1620 there. So 16 over the 1620. T over the 1620. I'll have to disconnect for a second. Okay, so this should fix this. So T over 1620. Okay, so I know that the final value is 20 grams. Okay, it tells me if the final is 20. We're trying to find P naught. Let me have this here. Well, actually, we do know that T, the time we said is 500. So you can use, I mean, we can just use the calculator here. You don't have to graph or anything. So on the basic calculator, I'm going to type in this 1/2. So 1/2 to the power of 500 over 1620. And that's going to give us 0.807. So if we go back to here, we have 20 equals P naught times 0.807. So now I can just do 20 divided by that answer. We should get a final answer for our initial amount as 24.783. You divide it by that. And that would just be grams. Okay, so that was an example where we had to find the initial because we could just solve and type this in here. And when we did 20 divided by our 0.807, you get 24.783 grams.